Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of elementary number theory. My name is Azmat Ali. In today's lecture, we will discuss problems 2.3. In this lecture, we will discuss first 5 questions. So to understand today's lecture, we first need to emphasize the definition of divisibility. So let us begin by repeating the definition of divisibility once. We say if we have a two integer a and b, then we call a is a divisor of b or b is divisible by a if there exists an integer m such that we can write b is equal to a times m. So this is the definition of divisibility. In question number 1, we have the statement if a divides b, this is given. Then we have to show that minus a also divides b, a divides minus a divides minus b. So it is given that a divides b. So by definition of divisibility, there exists an integer m such that we can write b is equal to a times m. This is the definition of divisibility. Now I have to prove that minus a also divides b. When this will be possible? This will be possible if I can write b is equal to minus a into m. So can I write one as we can write b is equal to minus a into minus m, because when you multiply a and m both by minus 1, the question number 1 will not change. As minus m is also an integer, so this equation completes the definition of divisibility. So we can say that minus a divides b for this integer minus m. In other words, you can say that this equation represent b is dividend and minus a is my divisor, and there exists an integer minus m such that when I multiply minus m with minus a, this gives am which is equal to b, and that completes the definition of divisibility. Next we have to show that a divides minus b. We again write equation number 1 as minus b is equal to a times minus m, because at this time I have to show that a divides minus b. So this is possible that if I express minus b is equal to a times some integer, so I am writing b is equal to am as multiply m with minus and b also with minus 1. So when you cancel out minus with minus, you can get the equation number 1. So this equation represent that a divides minus b. Lastly, I have to show that minus a divides minus b. So again we can write, because at this time we have to show that minus a divides minus b, so I will take minus sign with a rather than m, and my dividend is minus b, so we will take minus sign with minus b. So I can write the first equation is b is equal to am as minus b is equal to minus a into m, and this shows that minus a divides minus b, and this completes the question number 1. Next, question number 2 is given that if a, b, c, d are 4 integers, we have to verify that if a divides b, then a divides the product bc. Given a divides b, it means there exists an integer m such that I can express b is equal to a times m. As c is also an integer, and I have to show that a divides bc. So we multiply the question number 1 with c to make here bc. So multiply 1 by c on both sides. We have BC is equal to A into MC. As M and C both are the integers, so their product is also an integer. So let MC is equal to a new integer M dash. So when we replace MC is equal to M dash, we have BC is equal to A times M dash. So this fulfills the definition of divisibility for this integer M dash, and we can say that A divides BC. In the second part of question number 2, we have to show that if A divides B and A divides C, then the square of A divides the product BC. So firstly, we will use both of the definition of A divides B. A divides B says that there exists an integer M1 such that we can express B is equal to A times M1. This is my first equation. The second information is A divides C, so I can write C is equal to A times M2 for integer M2 belong to Z. As in our requirement, we can see that this is A square. So when this is possible, when we multiply question number 1 with question number 2, on the right hand side we can get A square, while we also need BC. So when we multiply question 1 and 2, we can get BC also. So multiply question number 1 and 2 side by side, we have BC is equal to A square into M1 into M2. As M1 and M2 both are the integer, so we suppose that the new their product is also an integer, and we say this is a new integer M3. So replace M1 into M2 is equal to M3, and this is equal to BC equal to A square into M3, and this fulfills the definition of divisibility. This shows that A square divides BC. In the C part, we have to show that if A divides B, this is possible if and only if AC divides BC where C is a non-zero. Given that A divides B, this implies we can write B is equal to AM by definition of divisibility, where M belongs to Z. As we need, we have to make BC here, so multiply on both sides with C. We have BC is equal to AC into M. This shows that AC divides BC. And for its converse, we will assume that AC divides BC, it means there exists an integer M such that we can write BC is equal to AC into M. By cancelling out C on both sides, we have the same equation as above, or in other words, you can reverse the sign here to find a necessary and sufficient condition. In the D part, we have to show that if A divides B and C divides D, then the product AC divides the product BD. Firstly, by using the condition A divides B, we have B is equal to A times M1. Similarly, when we use C divides D, this gives D is equal to C times M2. Multiply 1 and 2 both sides. Multiply 1 and 2 side by sides. We have BD is equal to AC into M1 M2. As M1 and M2 both are the integers, so their product is also integer. So replace this product by the new integer M3. This shows that BC AC divides BD. Next, question number 3. This is also an interesting question. Prove or disprove if A divides the sum B plus C, then either A divides B or A divides C. In other words, in this question, we have to show that if an integer divides the sum of two integers, is it necessary that the integer A must divide either one of them? This is not necessary. That if A divides the sum B plus C, then either A divides B or A divides C. For example, let A is equal to 3, B is equal to 2, C is equal to 4. Then you can see that 3 divides 2 plus 4, that is A divides B plus C. But you can see that 3 neither divides 2 nor 4. Question number 4, this is a mathematical induction question. For n greater than or equal to 1, use mathematical induction to establish each of the following divisibility. 8 divides this vertical line. You know, this is called divisibility, line of divisibility. 8 divides 5 raised to power 2n plus 7. Firstly, we check the statement for n is equal to 1. By putting n is equal to 1 here, this gives 8 divides 5 square plus 7. 5 square, 25 plus 7, this is 32. That is 8 divided 32, which is correct. So statement is true for n is equal to 1. Suppose that the statement is true for n is equal to k. This means 8 divides 5 raised to power 2k plus 7. So by definition of divisibility is if 8 divides this sum, it means there exists an integer q such that we can express 5 raised to power 2k plus 7 is equal to 8 times q. Say this is star. Next we check the statement for n is equal to k plus 1. So for k is equal for n is equal to k plus 1, we have to show that 8 divides 5 raised to power 2 times k plus 1 plus 7. So firstly we consider the dividend, that is 5 raised to power 2k plus 1 plus 7. We can break the power 5 raised to power 2k into 5 raised to power 2 plus 7. Now to involve star, we add and subtract 5 raised to power 2 into 7. Actually now I have to use this star, and in this star the left side is this is my left side, which is 5 raised to power 2k plus 7. So I want to involve this side 5 raised to power 2k plus 7. So how can I involve this? When I add and subtract this factor 5 raised to power 2 into 7, we can get 5 raised to power 2k into 5 square plus 5 square into 7 minus 5 square into 7. So when you take 5 square as a common multiple, this gives 5 square into 5 raised to power 2k plus 7, and by taking common 7 from here, this gives 1 minus 25. 5 square is 25. By using question number 1, by using question star 5 raised to power 2k plus 7, this is equal to 8q, and this becomes minus 24 into 7. You can take 8 as a common. This gives 25q minus 21. 8 3 is 24, 3 into 7 21. So this shows that this number is a multiple of 8 because q is an integer. So 25q minus 21 is also an integer. Say this is equal to some new integer m. So this is 8m. So this implies that this number is equal to 8m. That shows that this shows that 8 divides the sum. So the statement is true for n is equal to k plus 1 whenever statement is true for n is equal to k. Hence by mathematical induction it is true for every positive integer. Next, in the b part we have to show that 15 divides 2 raised to power 4n minus 1. This is similar question as we have discussed in a part. Firstly we check statement for n is equal to 1. By putting n is equal to 1 here, we have 2 raised to power 4 into 1 minus 1, that is equal to 15. 15 divides itself, which is true. Suppose statement is true for n is equal to k. So this shows that 15 divides 2 raised to power 4k minus 1. It means 2 raised to power 4k minus 1 is equal to 15 times q. Say this is my star equation. Next we suppose that next we check that statement is true for n is equal to k plus 1. So consider the dividend, that is 2 raised to power 4k plus 1 minus 1, that can be obtained by just replacing n is equal to k plus 1 in the original statement. So now I have to show that this number is divisible by 15. So by breaking the exponent here, this becomes 2 raised to power 4k into 2 raised to power 4 minus 1. To involving the same factor, that is 2 raised to power 4k minus 1, I can add and subtract the number 2 raised to power 4 here. So when you add and subtract this number 2 raised to power 4, we have 2 raised to power 4k minus 2 raised to power 4 minus 2 raised to power 4 plus 2 raised to power 4 minus 1. By taking common 2 raised to power 4 from these two terms, this gives 2 raised to power 4 into 2 raised to power 4k minus 1, and this becomes 15. By using star, this is equal to 15q. By taking 15 common, so this becomes 15 into 16q plus 1. As 16q plus 1 is an integer, say this is equal to m. This shows that the number is divisible by 15. Hence the statement is true for n is equal to k plus 1 whenever it is true for n is equal to k. Hence by mathematical induction, statement is true for every positive integer. In the c part, we have to show that 5 divides the sum of these two integers. For n is equal to 1, This gives 3 raised to power 4 plus 2 raised to power 2, that is 85. 5 divided 85, this is correct. Suppose that the statement is true for n is equal to k, that is 5 divided 3 raised to power 3k plus 1 plus 2 raised to power k plus 1. It means there exists an integer q such that we can write 3 raised to power 3k plus 1 plus 2 raised to power k plus 1 is equal to 5k. Say this is my star. Next we check that the statement is true for n is equal to k plus 1. So when you replace here k is equal to k plus 1, this becomes 3 raised to power 3 into k plus 1 plus 1, 2 raised to power k plus 1 plus 1. Now I have to show that this whole sum is divisible by 5. By multiply 3, we have 3 raised to power q plus 4. This is 2 raised to power k plus 2. We can break this exponent 3 raised to power 3k plus 1 into 3 raised to power 3, 2 raised to power k plus 1 into 2. We can write 3 raised to power 3 is equal to 27. This becomes 27 into 3 raised to power 3k plus 1 plus 2 into 2 raised to power k plus 1. Now say this is my double star. Now at this point students may be confused at which number or factor we have to add or subtract here. I am giving a very shortcut and easy trick. We just find the value of any of the factor 3 raised to power 3k plus 1 or 2 raised to power k plus 1 from star. This is my star. If I find the value of this factor 3 raised to power 3k plus 1, this is equal to 5q minus 2 raised to power k plus 1. That is 3 raised to power 3k plus 1 is equal to 5q minus 2 raised to power k plus 1. Substitute this value of 3 raised to power 3k plus 1 in double star. Simple. This is a very simple and easy technique. There is no need to think that which factor we should add or subtract here. So this gives 27 into 5 raised to power 5 into q minus 2 raised to power k plus 1 plus 2 into 2 raised to power k plus 1. Multiply by 27, we have 27 7 into 5q minus 27 into 2 raised to power k plus 1. This is 2 into 2 raised to power k plus 1. By adding these two terms, this becomes minus 25 into 2 raised to power k plus 1. By taking common 5, we have 27 into q minus 5 into 2 raised to power k plus 1. This, as q is an integer and k is also an integer, so for every k greater than or equal to 1, this whole number is also an integer. So say this is equal to m. So this shows that the number is multiple of 5, that is 5 divided by this number. Statement is true for n is equal to k plus 1, hence by mathematical induction statement is true for every positive integer. Next is question number, it's D part. I hope you can do this question by yourself. This is similar part to C. Yes, this is an interesting question. E part. In this question we have 3 terms. We have to show that this sum is divisible by 24. So first we check the statement for n is equal to 1. When you put n is equal to 1 here, this gives 24. This shows that 24 divided 24. Statement is true for n is equal to 1. Suppose that the statement is true for n is equal to k. And this becomes 24 divide this sum. It means there exists an integer q such that we can write this number is equal to 24q. So say this is a star. Next we check the statement for n is equal to k plus 1. So consider the expression 2 into 7 raised to power k plus 1 plus 3 into 5 raised to power k plus 1 minus 5. We can break this power 2 into 7 raised to power k into 7, 3 into 5 raised to power k into 5 minus 5. This is 2 into 4, 2 into 7, this is 14, and this is 3 into 5, this is 15, minus 5. Now again using, you can use the same technique as we discussed in above part. You can find the value of either of the factor 7 raised to power k or 5 raised to power k, but I am finding the value of constant here. If you find the value of 5 here, this 5 is equal to 24q minus 2 into 7 raised to power k minus 3 raised to power 5. minus 3 into 5 raised to power k. So plugging the value 5 here, we have 14 into 7 raised to power k plus 15 into 5 raised to power k minus, so sorry, this is the value of, yeah, the value of 5 will be minus 24 into q plus plus. So substituting this value 5 here, we have minus 24q plus 2 into 7 raised to power k, 3 into 5 raised to power k. So by adding and subtracting the terms, we have 12 into 7 raised to power k, 12 into 5 raised to power k, 24q. Taking 12 as a common multiple, we have 12 into 7 raised to power k plus 5 raised to power k plus 24q. Next, we can check that for every positive integer k greater than or equal to 1, this number 7 raised to power k plus 5 raised to power k is always an even integer. You can put any value of k, this will always an even integer. For example, if you put k is equal to 1, this becomes 7 plus 5 raised to power 1, that is equal to 12, which is an even integer. If you put suppose k is equal to 2, this becomes 7 square plus 5 square, that is 49 plus 25, which is equal to 74. Again an even integer. So in any case, this number is always an integer, even an integer. So suppose this is equal to 2m. So the last expression becomes 12 into 2m plus 24q, that is 24 into m plus q. M and q both are the integers, so their sum is also an integer. Say this is a new integer s, so this becomes 24s. This implies that this complete statement for n is equal to k plus 1 is equal to 24s, that is 24 divided this sum, and this shows that the statement is true for n is equal to k plus 1 whenever it is true for n is equal to k, hence the statement is true for every positive integer. Next we discuss the last question, question number 5. This is also very interesting question. In the question, author says that for any integer a, either it is positive, negative or 0, for any integer a, one of the integer a plus 2, a plus 4 is divisible by 3. This question intuitively you can check that it is true because suppose my a is 1, then a plus 2 will be 3, this is a plus 2, and a plus 4, this will be 1 plus 4, that is equal to 5. So you can check that in this progression 1, 3, 5, the central number is divisible by 3. Suppose if my a is 0, then a plus 2 is equal to 2, a plus 4 is equal to 4. Now 0 is divisible by 3. Suppose my a is negative number, suppose a is minus 7, then a plus 2 will be minus 5, a plus 4 will be a is minus 7, a plus 2 is minus 5, yes, and a plus 4 is equal to minus 7 plus 4, which is equal to minus 3, and minus 3 is divisible by 3. So it is correct for any 3 consecutive integer. So when you can check that these 3 numbers are actually in the arithmetic progression with a common difference 2. So it must be that thus any of the one of the number will be divisible by 3. And this is also true if you take any number, the sequence of these 3 integers a plus 1, a plus 2. Then you can again check that one of the number is also divisible by 3 again. So next we prove this question mathematically. When we divide an integer a by 3, by the division algorithm, we can write a is equal to 3q plus r. Suppose this is my a integer, I am dividing a by 3. I can find an integer q such that when we multiply 3 with q, we have 3q. By subtracting 3q from a, we have a remainder r. And your remainder r always lies between 0 and 3. Or you can write it as 0 less than or equal to r less than or equal to 2. So A can be written as in this form. Now we check for different values of R, which value of A is divisible by 3. So when you put R is equal to 0, my A is equal to 3Q. This shows that A is multiple of 3. So when your R remainder is 0, this shows that the number A is equal to 3Q is always multiple of 3. When your remainder is R is equal to 1, then A is 3Q plus 1. In this case, the central number A plus 2, that is 3Q plus 2. When you put A is equal to 3Q plus 1 here, we have 3Q plus 1 plus 2, that becomes 3Q plus 3. By taking 3 as a common, we have 3 into Q plus 1. This shows that this number is divisible by 3. Hence, in this case, A plus 2 is divisible by 3. And if your number A is of this form, 3Q plus 2, then the number A plus 4, that is 3Q plus 6, and this number is divisible by 3. So I hope now you have a clear understanding about today discussions. Still, if you have any query or a question, you can comments me or message me. Inshallah, I will reply you. So see you in the next lecture. In the next lecture, we will start from question number 6.